Welcome back. In this video, we'll talk about some methods that we can use to compare independent samples, again, using the t-distribution. Now, how we choose to compare independent samples depends on the assumptions that we're willing to make. So specifically, are we willing to assume that our data come from two separate populations with the same variance? Or are we safer assuming that they have different levels of variability? The answer to that question will affect how we do our calculations and come up with an answer to this question. After talking about how to answer this question of which assumption we should make, we'll introduce confidence intervals for the difference in two population means, as well as a test for the difference in population means. So let's start with some notation. We'll let xi represent the ith observation in group 1 and x2i represent the ith observation in group 2. We'll then denote the sample mean in each of these groups as x bar 1 for group 1 and x bar 2 for group 2, which may have different sample means, again, because they're no longer paired samples. These are independent. So x1 may be the sample size in group 1, N1 and N2 are the respective sample sizes. So then it turns out that this difference in sample means, x bar 1 minus x bar 2, happens to follow a t-distribution with mean mu1 minus mu2. Now, what about the standard error of this t-distribution? Well, this is where things get a little trickier. This is where we may have to make an assumption. So if we can assume that both groups have the same population standard deviation, that is that sigma 1 is equal to sigma 2, then we'll estimate the variability of this new distribution using what's called the pooled standard error formula. In R, we'll specify this by using the option var.equal true. If no, we'll use a formula called the unpooled standard error formula, or the Welsh approximation. To denote this in R, we will set var.equal to false. So we'll let R know which assumption we are making about the variability of our two populations using this var.equal statement. Now you can find the formulas for each of these standard errors in your textbook. However, since we really won't be calculating them by hand, I've chosen to leave them off the slides, but you're welcome to give those a look. Here is a rule of thumb. So when are we comfortable assuming that the variation of two populations is the same? When aren't we comfortable making that assumption? Well, if we take the larger of the two standard deviations, so denoted here S max, divide by the smaller of the two standard deviations, S min, if that ratio is greater than 2, then we should assume that the variances are unequal. However, if that ratio is less than 2, it's usually a fair assumption that the population variances may be the same. So given that, let's look at how we might calculate a confidence interval. Our confidence interval is going to look very similar. We'll take the sample means, x bar 1 minus x bar 2, calculate their difference, and since that's really what we're looking at here, is the difference of the means. We'll add and subtract some value from the t-distribution times the standard error. Now, again, this is one situation where calculating those standard errors gets really tricky. Calculating that t star, or the value from the t-distribution, will also get quite tricky. So in practice, we'll go straight to that t-test function if we have real data. In practice, depending on which assumption you use, the results are pretty similar. So there's often not that big a difference between assuming that the variances are equal versus assuming that they are not equal. So let's take a look at an example. According to the CDC, obesity rates among children have increased dramatically over the past 3 decades, from a low of about 5% up to 18% in 2010, so 10 years ago. A study examined the effect of family-based food counseling sessions provided by trained professionals. The study randomly assigned obese children aged 9 to 12 years to either the counseling intervention or a control group not receiving any food counseling. So our data set is in the obesity data set. We have two independent groups. Children were either assigned to receive food counseling or not. There's no connection or correspondence. So these are independent samples. Let's take a look at the data. So here we're looking at the change in weight after a 15-week period. So if the weight has increased or has a positive change, the children have gained weight. If there is a negative change, they have lost weight over those 15 weeks. Starting with the control group, the peak of this distribution is a little bit above 0. So it looks like on average, students in the control group may have had a weight gain. They may have gained weight over the 15-week period. Whereas looking at that intervention group here in blue, the peak of this histogram is on the negative side. So it looks like in the intervention group, on average, the children lost weight. Let's take a look at how the summary statistics compare. So how do the means and standard deviations compare? For the control group, the average weight change was positive 3.48 pounds, so on average they gained weight. In the intervention group, the average change was negative 2.3 pounds, so on average they lost weight. Looking at those standard deviations, in the control group the standard deviation is about 4.3, in the intervention group the standard deviation is about 5.2, so we have fairly similar variation between the two groups. So let's see what happens under both assumptions if we calculate a confidence interval. So here I am using conf.level to indicate that I want the confidence interval. The default assumption for var.equal is false. So if we don't include that var.equal true statement, automatically we will assume that that is false. Our confidence interval here, if we are not assuming equal variances, goes from a difference of 3.48 to a difference of 8.09 pounds. Here our control group comes first, followed by our intervention, so the control group's change is between 3 and 8 pounds higher than the intervention group. Now if we do assume equal variances here by adding that var.equal true statement, take a look at our confidence interval. It goes from about 3.3 to about 8.3. So it is slightly different, but not that different. If we look at unequal variances, 3.45 to 8.09, that interval is slightly smaller than the confidence interval, assuming that the variances are equal. So in most situations, it really won't make much difference which assumption we choose. There will be differences in the answers, but rarely will those differences be the kind that change our conclusion. So let's talk about how to do a hypothesis test. And because we've done a lot of hypothesis tests recently, we'll go through these steps fairly quickly. So our first step is to write the null and alternative hypothesis. Here our null hypothesis is that the difference in population means is equal to some value, say mu naught, mu 0. Most of the time this value is itself 0. The difference in population means is less than, greater than, not equal to will be our alternative hypothesis. Again, we're usually comparing this difference to, say, 0. We'll calculate our test statistic by taking the sample, the difference in the sample means minus mu 0, usually 0, divide by whichever standard deviation we choose to use. We'll determine the p-value, again using t.test here, with the appropriate assumption about the variances. And then our conclusion step is pretty much business as usual. So let's take a look at how we would set up a hypothesis test for this obesity study. What we're looking at here is whether or not there is a difference in the weight change. And we might expect that the control group would be more likely to have a higher change in weight, because the higher that number, the more weight gained. So we might be looking at a greater than hypothesis. The mean weight change for the control group is greater than the mean weight change for the intervention group. Our t-stat here is about 5.001, so our sample difference is about 5 standard errors higher than what we would expect if these groups were the same. Our p-value is quite small, 0.000003, so we have some strong evidence to reject the null hypothesis. We can conclude that the mean weight change for the control group is higher than the mean weight change for the intervention group. In the next video, we will introduce a technique called analysis of variance, which really just extends this 2-sample t-test to more than 2 groups. We'll see you then.